Next up, we have Antonio Pensabene from the INAF in Bologna, who will be telling us about ALMA multiphase ISM.
Okay, I'm going to share my screen. Can you see it?
Yes.
Okay. So, hello everybody. I'm Antonio Pensabene, PhD student at INAF Astrophysics and Space Science Observatory at University of Bologna. First of all, I would like to thank all the organizers for giving me the opportunity of presenting my work in this very nice and exciting meeting. And today I'm going to show you some results on ISM characterization in quasars galaxies at redshift greater than 6 with ALMA. All the results that I'm going to show you are collected in a paper that was recently submitted thanks to the efforts of many people that are listed here, in particular Dr. Roberto De Carli, which is my PhD supervisor. This work is focused on two systems that I show you at the bottom of these slides. The systems are composed by a quasar and nearby companion galaxies in the proximity. The systems are PJ 38-21 are redshift 6.2 roughly, and PJ 23-20 are redshift 6.5. Here you can see recent ALMA high resolution C+ observation, in which you can clearly distinguish the emission from the quasar and the emission from the companion galaxy. This project is based on a serendipitous discovery of various quasar-host companion galaxy pairs at redshift greater than 6, published in De Carli and collaborators paper in 2017. And the very interesting aspects of these systems is that the companion galaxies do not show evidence of AGN activity as revealed by near-infrared observation. Therefore, these systems are a perfect laboratory in order to study the interplay between black hole growth, star formations in massive galaxies as they emerge from cosmic dawn. Okay, the cold gas emission in quasar host at high redshift is typically studied by using bright tracers of the ISM, such C+ or C+ atomic phase traction line, or CO rotational lines. However, we have to keep in mind that the ISM is a very complex environment composed by different phases exposed to a variety of physical conditions. Therefore, in order to dissect the different phases of the ISM, we need to target a sample of far infrared diagnostics. For this reason, I started on already collected ALMA cycle 3, 5, and 7 observation that target 11 main emission lines, as well as far infrared continuum that trace the dust emission in these two systems that I told you before. Okay, here I briefly show you all the detection that we have, starting from the system PJ 23-1-20. Here you can see very nice detection of N+ line in both quasar and companion galaxy. N+ is typically associated to the full luminous phase of the ISM. We also have CO 726 and C1 in both of the systems that are associated to molecular and atomic medium, respectively. We also have multiple CO line at IJ, in particular in the quasars, but not in the companion, and this is a very first evidence of less excited medium in the companion galaxy compared with respect to the quasar host. Then we also have 3 H2O lines detections that are very interesting lines because they trace the warm dense phase of the ISM, for which there is very little information at such high redshift. Unfortunately, we don't detect this line in the companion galaxy. And finally, we also have a very nice OH doublet in both the galaxies. For the other system, PJ 38-21, unfortunately, we only have sparse detections, and this is due to the fact that the ALMA program was not completed. Therefore, all the results that I'm going to show you in the next slide are mainly focused on the previous systems, not this. Here you can see the continuum maps in 4 frequency setups for these systems and only 2 in the other one. As you can see, our observations were designed in order to not resolve the emission in the single sources, but with high enough angular resolution in order to disentangle the companion galaxy from the quasar host. Okay, we started by combining all the information about far-infrared continuum in the different ALMA bands, and in order to put quantitative constraint on dust properties. To do this, we modeled the dust spectral energy distribution by using a modified black body, also taking into account the effect of the CMB, that is a very important source of heating and a background source against which we measure the line and the continuum emission. And we also assume a typical dust temperature of 47 Kelvin. This is typical dust temperature observed in a redshift quasar. And this is required to break the degeneracy between three parameters due to the lack, essentially, due to the lack of data point near to the peak of the dust SED. By doing this, we retrieved the estimate of dust masses and spectral emissivity index in both quasar and companion galaxies. And for this latter source, we also considered an additional scenario with lower dust temperature in order to take into account the lack of a strong AGN in this source. We also did the same thing on the other systems, but in this case, as you can expect, the constraints on the dust parameters are shallower due to the lack of data point, essentially. Okay, then we tried to put also quantitative constraint on the physical properties of the different phases of the ISM. And to do this, we ran a set of models using cloud irradiating transfer codes in order to simulate the typical photo and X-ray dominated region. Cloudy solves basically the radiative transfer equation across the cloud, predict the line intensity as they emerge from the cloud surface. And we ran these models by varying two main parameters, the hydrogen volume density of the cloud and the strength of radiation field at which the clouds are exposed, in two cases, PDR and XDR regime. Then we compared our observation with cloudy predictions in order to put constraints on the parameters. We started with C plus over C1 line ratio. That is a powerful tool in order to distinguish the PDR from XDR regime. As you can see, our observation, the colored area and lines were reproduced by cloudy models in PDR regimes. By also combining other information, for example, C1 over total infrared luminosity, C plus over total infrared luminosity, we can, as you can see, we can put a good constraint, order of magnitude constraint on the strength of radiation field, of local radiation field, and exclude the XDR regime, of course. Then we can study, for example, the fraction of C plus arising from the PDR. To do this, we assume that typical C plus over N plus ratio of 3 that is typically observed in H2 regions. With this assumption, we computed the fraction of C plus arising from the neutral medium. And the main result here is that the neutral medium can account for almost all C plus emission, both quasar and companion galaxies of our study. Then we can also combine all our CO lines in order to study the CO spectral energy distributions and compare them with those of local starburst and AGN and other high redshift quasars. As you can see, for example, one of our quasars, the gold circle, are roughly consistent with the CO sled, average CO sleds of the local AGN and other redshift quasars, while for the companion galaxies, the pink circle, the CO spectral energy distribution appear less excited, more similar to the local starburst galaxy. As I told you before, the lack of IJ CO line detection suggests us that the companion galaxies ISM are less excited than the ISM in quasar host. Then we can also try to perform a fit of our CO spectral distribution. Here you can see the cloudy models, and the very different between PDR and XDR regime are in the IJCO lines that are more excited in the XDR regime. By using these models, we can try to perform a fit of one of our CO sled by using a composite model with a PDR that takes into account the emission of low JCO line and XDR that dominates at IJ. And the result is that the PDR account for almost all the molecular mass and the low JCO lines, likely associated to an extended gas reservoir, while high JCO lines are dominated by XDR that likely arise from central region quasar host. Okay, then we can try to do similar things by combining our H2O lines. At the top of this slide, you can see the prediction of H2O spectral energy distribution from cloudy, and at the bottom right, the best fit model. Here, the main result is that our model points to a medium with a high hydrogen volume density exposed to strong radiation field with high hydrogen column density. Therefore, H2O emission in these sources likely arise in the deep of molecular clouds. Then we can further explore the warm dense phase of the ISM in these sources, for example, by studying the relation between H2O luminosity and total infrared luminosity. As you can see, one of our quasars lie almost perfectly on this relation that is likely the consequence of infrared pumping mechanism that populate the higher level of this molecule. And then we can also study the H2O over OH line ratio. And with this ratio, we found basically similar results with respect to what we found with other tracers. So high density medium exposed to strong radiation field. Okay, to summarize, in order to dissect the physical properties of the different phases of the ISM, we need to target a sample of far infrared diagnostics associated to different phases of the ISMs. And we can also study the impact of black hole growth and star formation on the ISM or quasar host cosmic dome. Our results suggest that the ISMs in quasar host appear more excited than that of the companion galaxies. And another interesting aspect is that we can put quantitative constraint on the ISM physical properties, a redshift greater than 6 in quasar host, by employing a very simple, self-consistent radiative transfer model by varying only three parameters. Finally, I would like to end my talk with these slides, because we are very interested in the warm dense phase of the ISM. There is, as I told you before, there is very little information on this phase at such a high redshift. For this reason, we started an observational campaign with NOEMA interferometer in order to target multiple H2O lines in a sample of infrared bright quasar host. And this work is in progress in collaboration with Paul van der Werf from University of Leiden and, of course, Roberto De Carli. Okay, that's it for me, and thank you for your attention.
Thank you, Antonio. That was great. We have time for 2 questions. The first one is from Huanchen Chen, who asks, what is the thermal equilibrium timescale of dust heating? If the quasar is very young, does it require a non-equilibrium model?
Okay, this is a very good point. Actually, we did not explore this aspect. But for example, yes, of course, further investigation are needed. In particular, we have to consider other kind of model, for example, including shocks or including cosmic rays excitation. That's okay. I don't have an answer for this question about the dust heating time scale, but of course, it's a good point.
And the second question is kind of related. Do you run constant temperature cloudy models? How does temperature affect your cloudy calculations?
Okay, no, the cloudy model are not isothermal, but with the constant pressure and constant density. Sorry, constant density, not isothermal model.
Okay, thank you very much, Antonio.
Thank you.